copper bus bars generally do not need a specific listing when used as equipment grounding conductors in telephone switching offices. However, Article 250.118 of the National Electrical Code, or NEC, allows the use of solid copper bars, either insulated or bare, as equipment grounding conductors. Article 110.3b states that electrical equipment and materials must be listed for their intended use unless specifically exempted. Although a listing is not usually required for copper bus bars, they should be made and installed according to accepted electrical safety standards such as UL Standard 467, which is the safety standard for grounding and bonding equipment. Some equipment manufacturers might require that listed bus bars be used for grounding their equipment. If this is the case, it is important to follow what the manufacturer says. Local authorities having jurisdiction, or OJs, may have extra requirements for using copper bus bars. It is best to check with the HA for any local rules. If listed copper bus bars are needed, you can buy them from well-known electrical suppliers and manufacturers, for example, Cooper Power Systems, Eaton Corporation, and Panduit Corporation. It is possible to have custom-made bus bars made at electrical shops, but it is important to make sure they meet certain criteria. Firstly, they need to be made of pure copper. Secondly, they need to be the right size and thickness for what they will be used for. Thirdly, they need to be properly cleaned and prepared for installation. Fourthly, they need to be marked with the manufacturer's name or some other way to identify them. Let's delve further into the National Electrical Code, or NEC, requirements related to grounding and bonding to fully understand the context of copper bus bars. Article 250 provides comprehensive guidelines for grounding and bonding electrical systems to ensure safety and minimize electrical shock hazards. The primary goal of grounding is to create a low impedance path for fault currents to return to the source, allowing overcurrent protection devices to operate and clear the fault quickly. This reduces the risk of electrical shock and fire. Grounding electrode systems are a crucial part of the overall grounding system. These systems consist of various grounding electrodes, such as ground rods, ground rings, metal underground water pipes, and building steel, all bonded together to form a common grounding point. The effectiveness of the grounding electrode system depends on the soil resistivity in the contact area between the electrodes and the earth. Lower soil resistivity and larger contact areas result in low ground resistance, which improves the performance of the grounding system. Bonding is the process of connecting non-current carrying metal parts of electrical equipment and enclosures to create an electrically conductive path. This path ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock if a fault occurs. Article 250.92 and 250.96 outline the requirements for bonding different types of metal enclosures and equipment. The size of the grounding and bonding conductors is determined by the size of the overcurrent protection device protecting the circuit. Table 250.122 in the NEC provides guidance on selecting the appropriate conductor size based on the rating of the overcurrent device. It is important to use the correct size conductor to ensure that it can safely carry the fault current without overheating or melting. Equipment grounding conductors, or EGs, are used to connect the non-current carrying metal parts of equipment to the grounding electrode system. These conductors provide a low impedance path for fault currents to return to the source. Article 250.118 lists the acceptable types of EGC, including wire, cable, and metal racers. As previously mentioned, solid copper bars are also permitted as EGC under certain conditions. Grounding and bonding are essential for maintaining the safety and reliability of electrical systems. Proper installation and maintenance of these systems are crucial for preventing electrical shocks, fires, and equipment damage. In addition to the NEC requirements, several other standards and guidelines provide valuable information on grounding and bonding practices. These include IEEE Standard 142, also known as the Green Book, which offers recommendations for grounding industrial and commercial power systems. Another useful resource is UL Standard 467, which specifies the requirements for grounding and bonding equipment. Understanding these standards and guidelines can help ensure that electrical systems are properly grounded and bonded, minimizing the risk of electrical hazards. Copper bus bars are often used in electrical panels, switchboards, and other electrical equipment to distribute power and provide a common grounding point. The size and ampacity of the bus bar must be carefully selected to handle the expected current load. Bus bars are typically made from high conductivity copper to minimize voltage drop and heat generation. When installing bus bars, it is important to ensure that they are properly supported and insulated to prevent accidental contact with other metal parts. The connections to the bus bar must be tight and secure to minimize resistance and prevent overheating. Regularly inspect bus bars for signs of corrosion, damage, or loose connections. Clean and tighten connections is needed to maintain optimal performance. Now let's focus on the practical aspects of using copper bus bars in grounding systems. Selecting the appropriate size and thickness of the copper bus bar is crucial for ensuring that it can safely carry the expected fault current. The NEC provides guidelines for determining the minimum size of grounding conductors based on the size of the overcurrent protection device. However, it is often necessary to use a larger conductor than the minimum requirement to account for factors such as voltage drop and future expansion. When calculating the required size of the copper bus bar, it is important to consider the following factors. Firstly, the available fault current at the point of installation. Secondly, the length of the bus bar. Thirdly, the allowable voltage drop. And fourthly, the ambient temperature. The available fault current is the maximum current the bus bar is likely to carry during a fault condition. This value can be obtained from a short circuit study or from the utility company. The length of the bus bar affects the voltage drop and the overall impedance of the grounding path. Longer bus bars will have higher impedance and will require a larger cross-sectional area to maintain an acceptable voltage drop. The allowable voltage drop is the maximum voltage drop that can occur along the bus bar without affecting the performance of the equipment connected to it. The NEC recommends limiting the voltage drop to 3% for branch circuits and 5% for feeders. The ambient temperature affects the ampacity of the copper bus bar. Higher temperatures reduce the ampacity of the conductor, so it is important to direct the conductor accordingly. Once you have determined the required size of the copper bus bar, it is important to select a bus bar that is made of high-quality copper and that meets the relevant industry standards. Copper bus bars are typically made from electrolytic tough pitch, or copper, which has a conductivity of 100% IX, or International Annealed Copper Standard. The bus bar should also be free from defects and imperfections that could compromise its performance. When installing the copper bus bar, it is important to follow the manufacturer's instructions and to use proper installation techniques. The bus bar should be securely mounted to a non-conductive surface and should be properly insulated to prevent accidental contact with other metal parts. The connections to the bus bar should be tight and secure to minimize resistance and prevent overheating. It is also important to protect the bus bar from corrosion by applying a suitable corrosion inhibitor. Regular inspection and maintenance of the copper bus bar are essential for ensuring its continued performance and reliability. Inspect the bus bar for signs of corrosion, damage, or loose connections. Clean and tighten connections as needed to maintain optimal performance. If the bus bar is damaged or corroded, it should be replaced immediately. In addition to the technical aspects of copper bus bars, it is also important to consider the safety implications of working with these components. Copper bus bars can carry high currents and voltages, so it is essential to take proper precautions to prevent electrical shock. Always de-energize the bus bar before working on it and use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Follow lockout-tagout procedures to ensure that the bus bar remains de-energized while you are working on it. Be aware of the potential hazards associated with working with copper bus bars and take steps to mitigate those hazards. By following these safety precautions, you can minimize the risk of electrical shock and ensure a safe working environment. Furthermore, let's expand on the topic of custom-made bus bars and the criteria they must meet to ensure safety and compliance. When fabricating custom bus bars, it is imperative to adhere to strict quality control measures to guarantee their performance and reliability. The selection of the appropriate copper material is paramount. As mentioned earlier, electrolytic tough pitch, or ET, copper is the preferred choice due to its high conductivity and purity. The copper should conform to ASTM BO 187, which specifies the standard requirements for copper bar, bus bar, and shapes. The dimensions of the bus bar, including its width, thickness, and length, must be carefully calculated to accommodate the expected current load and voltage drop. Use appropriate engineering formulas and software to determine the optimal dimensions for the specific application. The bus bar should be free from sharp edges, burrs, and other imperfections that could cause stress concentrations or electrical arcing. Deburr and polish the edges of the bus bar to ensure a smooth, uniform surface. The surface of the bus bar should be thoroughly cleaned to remove any dirt, grease, or oxidation. Use a suitable cleaning agent and a clean cloth or brush to prepare the surface for installation. If the bus bar is to be plated or coated, ensure that the plating or coating is applied evenly and that it adheres properly to the copper surface. Use a reputable plating or coating company and follow their recommendations for surface preparation and application. The bus bar should be marked with the manufacturer's name or logo, the material type, the current rating, and any other relevant information. Use a permanent marking method, such as etching or stamping, to ensure that the markings are legible and durable. The bus bar should be properly packaged to protect it from damage during transportation and storage. Use a sturdy container and protective padding to prevent scratches, dents, or other damage. Provide clear instructions for handling and installation. The manufacturing process should be documented to provide a record of the materials used, the dimensions, the surface finish, and any other relevant information. Maintain a quality control system to ensure that all bus bars meet the required specifications. In addition to these criteria, it is also important to consider the specific requirements of the application. For example, if the bus bar is to be used in a corrosive environment, it may be necessary to use a corrosion-resistant copper alloy or to apply a protective coating. If the bus bar is to be used in a high-temperature environment, it may be necessary to direct its current carrying capacity. By following these guidelines, you can ensure that custom-made bus bars meet the required safety and performance standards. Remember, working with electrical equipment can be dangerous. Always take the necessary precautions to protect yourself from electrical shock and other hazards. Consult with a qualified electrician or engineer if you have any questions or concerns about the design, fabrication, or installation of copper bus bars. Let's talk about testing and inspection, and why they are crucial for ensuring the reliability and safety of copper bus bars. After manufacturing or installation, copper bus bars should undergo thorough testing and inspection to verify that they meet the required specifications and are free from defects. Here are some common testing and inspection methods. Firstly, visual inspection. This involves carefully examining the bus bar for any signs of damage, corrosion, or imperfections. Look for cracks, dents, scratches, sharp edges, and other irregularities. Secondly, dimensional verification. This involves measuring the dimensions of the bus bar to ensure that they are within the specified tolerances. Use precision measuring tools such as calipers and micrometers to verify the width, thickness, and length of the bus bar. Thirdly, conductivity testing. This involves measuring the electrical conductivity of the copper material to ensure that it meets the required standards. Use a conductivity meter to measure the conductivity of the bus bar and compare it to the specified value. Fourthly, insulation resistance testing. If the bus bar is insulated, this involves measuring the insulation resistance to ensure that it is adequate to prevent electrical leakage. Use a megometer to measure the insulation resistance between the bus bar and ground. Fifthly, high pot testing. This involves applying a high voltage to the bus bar to verify that it can withstand the specified voltage without breaking down. Use a high pot tester to apply the test voltage and monitor for any signs of arcing or insulation failure. Sixthly, thermal imaging. This involves using a thermal imaging camera to detect any hot spots or areas of excessive heat on the bus bar. Hotspots can indicate loose connections, overloaded conductors, or other problems that could lead to failure. Seventhly, ultrasonic testing. This involves using ultrasonic waves to detect internal defects or flaws in the copper material. Ultrasonic testing can reveal cracks, voids, and other imperfections that are not visible to the naked eye. The frequency and extent of testing and inspection should be based on the criticality of the application and the potential consequences of failure. For critical applications, more frequent and comprehensive testing may be required. All testing and inspection results should be documented and maintained for future reference. Any defects or discrepancies should be addressed promptly and effectively. By implementing a robust testing and inspection program, you can ensure that copper bus bars meet the required standards and perform reliably throughout their service life. This will help to prevent electrical failures, improve safety, and reduce downtime. Remember, proper testing and inspection are essential for maintaining the integrity of electrical systems and protecting people and property from electrical hazards. Finally, let's talk about the importance of regular maintenance of copper bus bars to ensure their long-term reliability and safety. Copper bus bars, like any other electrical component, require periodic maintenance to prevent corrosion, looseness, and other problems that could lead to failure. Here are some key maintenance practices. Firstly, visual inspection. Regularly inspect copper bus bars for signs of corrosion, dirt, or damage. Look for discoloration, pitting, or the presence of foreign materials. Secondly, cleaning. Clean copper bus bars with a soft cloth and a mild cleaning solution. Avoid using abrasive cleaners or solvents, as these can damage the copper surface. Thirdly, tightening connections. Check all bolted connections on copper bus bars and tighten them as needed. Use a torque wrench to ensure that connections are tightened to the manufacturer's specified torque. Fourthly, corrosion protection. Apply a corrosion inhibitor to copper bus bars to protect them from corrosion. Use a corrosion inhibitor that is specifically designed for use with copper. Fifthly, insulation testing. If the copper bus bars are insulated, test the insulation resistance periodically to ensure that it is still adequate. Use a megometer to measure the insulation resistance. Sixthly, thermal scanning. Use a thermal scanner to check for hot spots on copper bus bars. Hot spots can indicate loose connections or overloaded conductors. Seventhly, replacement. Replace copper bus bars that are damaged, corroded, or otherwise defective. Use replacement bus bars that meet the original manufacturer's specifications. The frequency of maintenance should be based on the environment in which the copper bus bars are installed. Bus bars that are installed in harsh environments, such as those with high humidity or corrosive atmospheres, will require more frequent maintenance. Keep records of all maintenance activities, including the date, the type of maintenance performed, and the results of any tests or inspections. Regular maintenance of copper bus bars can help to prevent failures, extend their service life, and improve the safety of electrical systems. Neglecting maintenance can lead to costly repairs, downtime, and even electrical hazards. Remember, proper maintenance is an investment in the long-term reliability and safety of electrical equipment. Consulting with qualified electrical professionals for guidance on maintenance practices and schedules is always recommended. Their expertise can help tailor a maintenance plan that suits the specific needs and conditions of the installation, ensuring optimal performance and safety.